Hello and welcome to this first SAT-scan tutorial about the purely spatial scan statistic. My name is Martin Kulldorff and I'm the developer of both the methods and the SAT-scan software. And we'll talk about first the purpose and then the methods, and then we'll give some examples with cancer data. So thank you for joining us. In epidemiology, there are two ways we use spatial statistics. One is if we want to study a specific hypothesis. You want to evaluate the relationship between some disease and some geographical variable, like radon, for example. And that requires a certain type of methods where we then adjust for the geographical variation. In disease surveillance, it's sort of the other way around. We evaluate the geographical variation of the disease, but we might adjust for certain things like age or gender or income. And SAT-scan only deals with the latter of these two, disease surveillance. So for the first type of problems, we shouldn't use spatial scan statistics or SAT-scan software. So what are some of the reasons for geographical disease surveillance? Well, one is to do outbreak detection. It could be infectious diseases, or it could be some chronic diseases. It might provide clues about disease etiology. It can be used to monitor diseases and preventing its spread. It can be used to evaluate health services, which might vary geographically, or it can be used for public education. And in rare cases, it could be used to detect new diseases. For example, both AIDS and Lyme disease was found out through geographical clusters or variants of diseases. So some of the example questions is there a salmonella outbreak somewhere? Are people in some geographical area at higher risk of brain cancer, which could be due to environmental risk factors or genetic risk factors? Are there geographical differences in the access to or the use of early detection programs like mammography screenings? Or are there geographical differences in the access to and the use of prostate cancer treatment? So those are some sample questions for geographical disease surveillance. We can have different type of data. So it could be count data, like new or prevalent cases of a disease, hospitalizations, or mortality. It could be categorical, like cancer stage or histology, or different treatments, or it could be continuous, like survival after diagnosis, or lead levels in the blood of children, for example, or BMI. And the data could be either very granular, like the exact location of where people live, or it could be aggregated to counties or zip codes or census tracts. And less aggregation is always better from a statistical and analytical point of view, but it's not always possible. Sometimes data is only available at aggregation levels. So here's Iowa breast cancer incidents from the 1990s. These are age-adjusted relative risk. So the question is this just a random pattern? Or are there any clusters on this map? Because by chance, there will always be some randomness. So to the naked eyes, we can sort of see some kind of patterns here, but is it just random, or is there truly some area, some clusters here where they truly have an excess incidence of breast cancer? So if we look at the map like this, the relative risk of 2 could mean very different things in a large urban county or a small rural county. So in a large county, it would be maybe 2,000 cases when 1,000 is expected. So that's a pretty good estimate of the risk. But in a small rural county, maybe 2 cases when 1 was expected, which could easily happen by chance. So we have to take that into consideration when we have a map like this. So we could, of course, for each county, and there are 99 counties in Iowa, we could say that do just a test to see is this statistically significant. So that would be creating what's called a probability map with p-values. And if we do that, we find that there are 7 counties of the 99 that has a p-value less than 0.05. But there is a problem here. So here we map them, so we can see those 7 dots, and we have 6 smaller ones with 0.05, between 0.05 and 0.1. So with 99 counties, if 5% by chance are significant, then we expect 5. And sometimes it could be more than 5, like 7 or 8, or sometimes it could be less. So the fact that we saw 7 doesn't necessarily mean that this is not by chance, because we need to adjust for the multiple testing of looking at these 99 counties. So when we map rates or relative risks, it's very useful for descriptive purposes, but there's a problem. In a simple map, there's no statistical testing. In probability maps, there are multiple testing. So the solution is what StatsScan does. It's one statistical test for the whole map, adjusting for the multiple testing. So this is a test for spatial randomness. So by chance, there will always be some geographical patterns apparent to the naked eye. So the null hypothesis is that the risk of disease is the same in all parts of the map. And then we can adjust for covariates like age using indirect standardization. So what is a scan statistic? So in the simplest one-dimensional case, we have observations on a timeline. Here's 7 observations. And then we do a window that gradually scans along, and then we count the number it's in it. So here's 0, now it's 2, for a while it's 3, then 1, 0, 1, and so on. And the definition of the simple case is the maximum number of cases that is in the window as it moves along. Now, it's more complicated in the spatial setting. So in the spatial scan statistic, we have a regular irregular grid of centroids covering this whole region. And then we create an infinite number of circles around each centroid from a radius of 0 up to it includes 50% of the population at risk. So we have a collection of small circles, large circles in the east, west, north, and south. So here is just a small sample of the millions of circles that will be part of Iowa. And you can see that they're all overlapping of different sizes and different locations. So what we do then with the spatial scan statistic is that for each circle, we obtain the actual and expected number of cases both inside and outside the circle. And then for each circle, we calculate the likelihood function. And then we compare all those circles, and we pick the circle with the highest likelihood, which is the most likely cluster. That is the cluster that's least likely to have occurred by chance. Now, by definition, there will always be one of those circles which has the highest likelihood. So the question is then, is the likelihood so high that it's unlikely to be due to chance? So we do the statistical inference. And we do that by generating random replicas of the data under the null hypothesis of no clusters. So we condition the total number of cases, and then we distribute them randomly around across Iowa or whatever region we're doing, and based on the expected counts. So that's called Monte Carlo sampling or Monte Carlo hypothesis testing. And then what we do is we compare the most likely cluster in the real data set with the most likely clusters in each of 999 random data sets or some other number. And that's the likelihood ratio test. And then under the null hypothesis, each of these 1,999 plus 1 is equally likely to be at any position if you rank those likelihoods. So the probability that under the null, the probability that the one from the from the real data set is among the 50 highest is 5%, because 50 divided by 1,000. And the p-value is just the rank divided by 1,000 or divided by 999 plus 1. So if, for example, if the rank from the real data set is 24, then the p-value is 24 divided by 1,000. So let's see what happens if we use this spatial scan statistics on the data from Iowa. So are there any clusters here? We'll do all the circles. And we find that these are the 4 most likely clusters, and the most likely cluster was in the east with a p-value of 0.11. So not statistically significant. So that means that any part of this map could be just by chance. And we saw that the most likely cluster had a 8%, or at a risk of 1.08, so 8% excess risk. So if this was just random, we would expect that to happen somewhere on the map. So that means that this pattern, where you can probably find some clusters by the naked eye, there's truly no statistically significant cluster. So any part of this map could be just random, geographically random noise. So some of the properties of the spatial scan statistic is that it adjusts for the population density. So for example, there's obviously more breast cancer in Des Moines, Iowa, because it's a big city, but it adjusts for the population density through the expected counts. And it simultaneously tests for clusters of any size and any location, small, large, medium, north, south, east, west, and so on. And it does that accounting for the multiple testing of the thousands or millions of circles evaluated. It can also adjust for confounders like age or sex or socioeconomic status. The method can be used for exact locations if we knew the exact location of each person, or in this case, we have aggregated data to county level. And the more granular data is, the better in terms of the statistics and analysis. But it's not always available. And the method can detect clusters with exceptionally high rates, which we did for Iowa, but also low rates. So for example, for cancer incidence or mortality, we typically are interested in finding places where there's high rates, where there's a problem. But if we looked at the cancer screening, for example, we might be interested in low rates, where there's less screening than other places to know where there needs to be offer more opportunities for screening. So let's do another example, brain cancer mortality in the United States. Brain cancer is one of the least common cancers, but among children it's the second most common after leukemia. We don't really know too much about what causes brain cancer. There are a few known risk factors, but they explain only a small proportion of the total number of cases. So this is the map of the United States, or 48 of the states. And red are high rates of brain cancer mortality in kids, and the blue is about average, and the gray ones are low. So are there any statistically significant clusters for brain cancer mortality here? You can stop the video if you want and try to see if you can guess some areas there in California that might look pretty scary, but who knows? So we'll go on now and see what the SAT-scan software and the spatial scan statistics says about this. And we have 7 clusters here. The most likely cluster was in the Carolinas, and the second most likely was in Northern California. But if we look at the details, we see that none of these clusters were statistically significant. The most likely in the Carolinas had 86 observed, 51 expected for relative risk of 1.7. The California one is smaller, 16 observed, about 5 expected, with a relative risk of 3.3. But basically, any part of this map could be as due to chance, because the magnitudes of these clusters you would expect to see at least somewhere in the United States if it's all random. So the conclusion: no statistically significant clusters detected for children, and any part of the pattern seen on the riddle map may be due to chance. So what about adults? So red is high rates, dark blue is low rates, and the gray and light blue are about average. So you can stop the video again if you want to. I can give you one hint, and that's that is at least one statistically significant cluster on this map. So if you haven't stopped the map, or if you want to see what the answer is, so this is what SAT-scan says, that the most likely cluster was around Arkansas, northern Mississippi, western Tennessee area. The second most likely in the Carolinas. And the dark clusters here are the high rates. The blue ones are low rate clusters. So in this case, we were looking at both high and low rates simultaneously. We can look at women. Again, the most likely clusters are around the Arkansas area and the Carolinas. And we can see, though, that the relative risk is fairly modest, only 1.22 for the Arkansas cluster. But we have a large sample size here. So we have actually good power to detect clusters. So the p-value is quite low, 0.0001. If we look at the men, we see that the results is about the same. The number one cluster has moved a little bit towards Kentucky, includes most of Tennessee, but the second one is still in the Carolinas. And the relative risk is slightly less, 1.15 for the Kentucky cluster. So the conclusion here is that for adults, there are specific areas with higher or lower rates of brain cancer mortality that's unlikely to be due to chance. And we have similar patterns for men and women, even though these are independent analysis because no case is in both of those two analyses. The excess risk is very modest, typically less than 20%. There was one that was 22. And that could be due to some small geographical differences in cancer risk, but it could also be due to differences in treatment. Maybe some areas have better treatment than others, or it could also be differences in the coding of cancers, since these are so small. If the excess risk had been twofold or threefold, coding would be much less likely as an explanation for a cluster. And these areas might be good locations for further cancer studies, whether it's etiology or treatment for brain cancer. And it's important to realize that the exact borders of the detected clusters are uncertain. We don't know we know the general area, but not what the exact borders are. So this is the last slide. So some of the conclusions about spatial scan statistics in SASCAN is that they can detect clusters, but also, and that's equally important, they can determine that there is no clusters. So we don't have to worry about if there's a reported cancer cluster, for example. We can pinpoint the approximate location and size of significant clusters. It adjusts for the multiple testing, which means that if there truly is no clusters, then we have only a 5% probability chance of detecting a false positive cluster. And in 95% of the cases, with 95% probability, we will detect 0 clusters with a p less than 0.05. So we don't get an excess number of false positive, which is important. The SASCAN software is free. It can be downloaded from sascan.org. And the references to the methods and the mathematical formulas and further additional examples, both that we have done and that many others have done around the world, is in the reference list on that website. And this was the first video about the SASCAN software. And the second one will be on space-time scan statistics. So I hope to see you then again. So thank you very much for listening and have a good day.